So you can write conservation of energy this way. Just know that 9 times out of 10, this equation is going to be more complicated than this equation. I like this equation a lot more. And now one more thing. Let's talk about when energy is conserved. So when is energy conserved? It all comes down to if the forces acting on my object are conservative forces. So now let's talk about we can talk about the definition of conservative forces and non-conservative forces. In my opinion, it doesn't really help people because it's such a vague definition. And the classic thing that you're going to hear every time is that for conservative forces, the path doesn't matter. The change in energy will be the same regardless of the path, which then means for non-conservative forces, the path that the object takes matters. And I hate that definition because it's so confusing, honestly. Like, what do you mean the path? What do you mean by that? Well, let me give you an example. Let's say I want to climb a mountain. Let's say I have a mountain here, okay? And I start from the bottom and I want to reach the top. If I say that the path doesn't matter, it could mean I could take the path straight up. It means I could take kind of a long-winded path and get there. It could mean that I could shoot out of a cannon and land there. And in these cases, what I just drew, where the path doesn't matter, where I go from point 1 to point 2, if the path doesn't play an effect in how the problem plays out, then that's when we're talking about conservative forces. If you're telling me that I have a different energy at point 2, depending on if I take route 1, or I will say route A, route B, or route C, like if I have a different energy based on all 3 of these different routes, then it would be considered a non-conservative force. If this explanation didn't make sense, don't worry. I hate this explanation too, but it's, I have to cover it just because everyone's going to talk about it at some point. The better explanation, in my opinion, is actually talking about forces that are conservative versus forces that are non-conservative. And so now let's give some examples of conservative forces. So an example of a conservative force would be gravity. In other words, the path of an object affected by gravity does not matter. What I mean by that is I have here, if I have like multiple ramps, if I have one ramp that just goes straight down like this, if I have a ramp that kind of goes like this, and then if I have a more shallow ramp that very slowly reaches the bottom like that, if I take paths A, B, and C like this, and I have a ball here, and then the ball goes down each of these different paths, and you want to know which one has the greatest velocity at the bottom, it's very interesting because in this case, if gravity is the only force acting on this object, what physics tells us is that the speed at all 3 of these points for the ball is going to be the same. I know that's hard to believe. I'm trying to tell you that the speed of the object at point A is going to be the same as if it takes this path here, B, the same as it takes path C here. And I'm just going to tell you, yes, it's a fact. They all have the same velocity. I don't have a proof for it besides the conservation of energy formula itself, which I will be doing later in this lesson. But you kind of just have to take my word for it, honestly. And you'll see how the math works out in the end. But the cool thing about gravity is gravity is a conservative force, meaning that the path an object takes does not matter. Okay? The energy is going to be the same. Here's another way of thinking about it. Gravity is not going to add energy to the system. It's also not going to subtract energy to the system. Although this ball is going to speed up, the total energy in the system is going to stay the same. And the reason is, when gravity is causing this ball to go down the hill, energy is increasing, the velocity is increasing, but that's only because the potential energy decreases as the height decreases as it's going down the ramp. So the total energy in the system stays the same, but the value of the energy itself is a constant with gravity. Now let's give an example of a non-conservative force, And an example of a non-conservative force, the classic one is friction. So if I have friction, like these surfaces are now kind of rough and it causes the object to slow down, now we're going to have different energies at all three of these points. And the reason being, friction is going to take away energy from the system. In other words, it's going to convert it into things like heat and sound and put it into a form of energy that is not kinetic or potential energy, which means the final speed at the bottom of these ramps is going to be slower than the path for A, because friction is going to be touching it for the shortest amount of time. So friction does play an example of how it's non-conservative. It's taking away energy out of the system. Other examples of non-conservative forces include pushing and pulling forces. Those are the classic examples. And I'm sure there's other examples of non-conservative forces as well, but those are the most common. And then for conservative forces, again, these are forces that don't affect the total energy in the system. Those are going to be the normal force. So the normal force is conservative. It's not going to add or subtract energy from the system. And another force example would be a spring force, which we're not going to talk about really today. I can talk about it in another lesson. But the spring force is also going to be conservative. That's not going to add or subtract energy to the system. Okay, so now I think that does a good enough job explaining the differences between when we're talking about conservative, when energy is conserved, and when energy is not conserved. And today we are just talking about when energy is conserved. That's what we're going to focus on today. In a couple days we're going to focus on non-conservative forces.